Last time we started the discussion on variational inference. The main idea was we were looking at three different methods of computing the posterior. The first method that we looked in the class was Laplace approximation, where we say that the posterior is approximated as a normal distribution with a certain mean vector and a certain covariance matrix. The mean vector turned out to be the theta map, and the covariance turns out to be the negative inverse Hessian of the log joint, evaluated at theta map. The second method that we looked at was Markov chain Monte Carlo MC, where we generate samples from the log joint. We assume a certain burn-in period. After that, we assume that it reaches stationarity, and then we can directly plug in those samples to compute the predictive posterior. The third method, which we started looking in the previous lecture, was variational inference. Here we convert the inference problem, the posterior inference problem, as an optimization problem. We say that let's assume that our posterior was a Q distribution, generally assumed to be normal distribution, but you can pick up anything, which is parameterized by the parameter psi. So we are trying to find out that optimal parameter psi, which minimizes the scale divergence between Q and the posterior theta given t, P of theta given t. Right? But later on we discussed the problem that P of theta given d is never known to us. If P of theta given d were known to us, then why do we even need to compute an approximation Q? We then looked at the definition of the scale divergence. So firstly, we saw it's a divergence, it's not a distance. So it's not symmetric. Q given P will not be the same as P given Q. And we write this in the form of an expectation vector. Expectation over the logarithmic of Q over P of theta. And the expectation is with respect to Q. We then also looked at the Monte Carlo way to get this. So there we'll draw samples from Q, right? Theta I is drawn from Q, and then you plug in log of Q of theta I over log of Q over theta I over P of theta I, and then you average it over the n samples that you draw. That is the Monte Carlo way to approximate the scale divergence. We did this exercise in the previous lecture, where we took two normal distributions, Q and P, both are univariate normal distributions, and then we analytically computed the scale divergence between them, which comes out to be some expression like this. And we'd also confirmed the same using torch and TensorFlow probability, that this is indeed the scale divergence formula that they're using for two normal distributions. Post that, we looked at optimizing. So we'd seen how we can optimize the parameters of one distribution, of Q distribution, to make it as close as possible to P via the KL between Q and P. Right, so here we said that previous time we said that Q2 seems to be closer to P in terms of scale divergence, right? And we did confirm that the scale divergence between Q2 and P is much lesser. Then we said the next thing was to optimize the parameters of Q so that we can minimize the scale divergence between Q and P. So previously I had shown this via using raw parameters, location and scale, and then I'd use a training optimizer. But I also wanted today to show that you can also inherit from torch.nn.module. This makes it easier for you to just call things like model.parameters to get all the parameters there, as well as just to reuse the code which you wanted to. So here we wanted to reuse the train function which we had previously shown you. Right? This is from our own library Astra that we had shown. So this function just asks for some model inputs, outputs, loss function, optimizer, epochs, and if you want to output state dictionary or not. Just because we wanted to not write this training loop again, we wrapped the normal distribution. So we've mentioned the forward and the representation. Then the forward we are just doing, we get the raw scale, we take a soft plus over that to make it non-negative, and then we are just passing this to the normal distribution object. So we'd seen this last time, that in a very few iterations, we are able to optimize the location and the scale of a Q distribution so that it becomes very close to a P distribution. We can also see this via an animation. So we can see that with the initial parameters, Q location is 4 and the scale is 0.5. So the scale divergence between Q and P is quite high. Now, if you were to see the different iterations through the animation, you can see how the Q is varying, how the loss is going down. And after about 100 odd iterations, Q will exactly superimpose P and the scale divergence has gone down to 0. Right? So this is the optimization procedure which we follow in scale divergence. It's in variational inference. We are trying to minimize the scale divergence between a proposal, a guide, whatever you want to call a variational distribution Q, and the distribution which you know a priori, which is P. Then we also looked at the optimization or finding the scale divergence between two distributions from different families. So this is where we said we don't have an analytical closed form solution. Therefore, we need, so this is our P distribution. It's a mixture of Gaussians. And if we try to find out the scale divergence between this and a Q distribution, which is a normal distribution, we get that scale divergence is not implemented because it does not exist in a closed form in an analytical way. But then we said that we can use scale divergence via MC sampling. So we, importantly, if you remember, the definition of scale divergence right? So it's expectation with respect to Q of log of Qm over P, right? So therefore, the samples you have to draw from Q, and then for those samples compute log of Qi minus log of Pi. That is exactly what we're doing. We find out first the sample set, which is we draw samples from Q, and then we do log of samples, Q dot log samples minus P dot log samples, and then you take the mean over them, 1 over n. So this gives you the Monte Carlo estimate. We confirm that if we did the Monte Carlo estimate, we get the value to be very close to if we did the analytical estimate. If we were to increase the number of Monte Carlo samples, the estimate will only get better. It's an unbiased estimator. And through this procedure, then we said that we can compute the scale divergence between Q distribution, which is a normal distribution now, and PS distribution, which is a mixture of Gaussians. Right? So analytically, this solution does not exist. But via Monte Carlo sampling, we can see that the scale divergence between Q1 and P, mixture of Gaussians, is lesser than the scale divergence between Q2 and P, and we can confirm that over here also. So the mixture of Gaussians is P. We can see that Q1 is a better fit to the mixture of Gaussians as compared to Q2, which is very flat. So last time we also then saw these figures where I was talking about the original formulation, which if we do Monte Carlo sampling and if we want to learn the location and scale of a normal distribution, we cannot backpropagate, right? Whereas if we convert this to the reparameterized form where we sample from the standard normal, we then multiply with the scale at the location, get the Z sample, and then compute the loss. Then through this, we are able to backpropagate towards optimizing the over location and scale. Right? So in this, I wanted to show you some more code. Because the computation graph is broken. Just hold on for a second, and through this new code that I've written, you should be able to understand. Right? So let's look at this code. I have a location which is a tensor. Scale is a tensor. Q is a normal distribution about the location and scale. I get a sample, right? S equal to Q dot sample. So I get a sample. I call the backward on the sample, right? If the gradients were flowing backwards, then I should be able to compute location dot grad and scale dot grad, right? If this were happening, but I get the error that does not have a grad function, does not require grad, etc., something like that, right? This is happening because in this particular case, when we call dot sample, it is breaking the computational graph for you, right? So let's look at what we saw previously, which is looking at the reparameterized form of this thing, right? So carefully look at this code where the computation graph is breaking. How can we fix this problem? What is the reparameterization here? What lines of code will we change? You take a standard normal. Okay. Multiply the sample with. We don't multiply distribution with something. So I've manually set a seed. We'll see in a minute why I've set the seed. I have a standard normal, which is location 0, scale 1, and I have my location and scale as what I had previously. I get a sample from the standard normal, which is EPS. I write Z equal to location plus scale into epsilon. This is the reparameterization, right? And let's just stop here for 1 second. I have Z dot backward. Right? So if I call Z dot backward, can you work this out in your notebooks? What is scale dot grad and what is log dot grad? You have everything available on the screen to compute this. When I call Z dot backward, if the computational graph is not broken, then I would be able to compute location log dot grad and scale dot grad. I want you to tell me those values. Just 1 second, I'll want everyone to complete. So Tash has given you a hint. Log dot grad should be del z by del log, and scale dot grad would be del z by del scale. Okay, so what is log dot grad? 1. Irrespective of the value of the location, you'll always get a 1, right? What is scale dot grad? Epsilon, right? So you are firstly able to see that you're able to compute the gradients this way, right? Now you are getting the answer in terms of epsilon, right? Previously, if you were to compute s dot backward, what do you get? You're not able to back propagate that way, right? Here you can see you have an equation right in front of you, which is showing you the back propagation capability. So gradient of location is 1, which we expect. Gradient of scale turns out to be 0.336, but this is also the same as epsilon value. Right? Does it make sense now? If I were to change the seed, you can always see that the gradient of the scale, which is scale dot grad, will be the same as the epsilon value there. So I have back propagation in front of you now. Move back to seed 42. Now, all of this that we have seen thus far, we could have also seen using something known as R sample. So in the first piece of code, I called dot sample. In the second one, I myself did the reparameterization trick. In the third version, I am instead of calling sample, I am calling just q dot R sample, right? And let me show you the result. With R sample, I still get the same result as expected, right? So what do you think R sample would be doing? Reparameterized sample, and this is the good thing about running code in VS Code about the capability to look up code. I will just command click, and I am given this. If you look at the path, Python 3.9 side packages starts distributions normal.py normal class. In that there is a R sample method. Can you see what this method is doing? EPS equal to underscore standard normals. It creates a standard normal of a specific shape and it multiplies that standard normal with a scale at the location, right? So can you see that whatever we have done is exactly the same as what is internally implemented, and you can see the difference between sample and R sample here, right? So now you have got some hint into how different methods are implemented. You can actually, now if you're interested, you may want to check if there are other distributions where the R sample method is implemented, reparameterization is implemented. You should maybe just go to distributions, maybe pick up some other distribution. Let's pick up beta and look at the properties that they have: mode, variance, R sample. The R sample here is calling Dirichlet.R sample. Why do you think they have implemented it this way? Why should a call to beta.R sample call Dirichlet.R sample? Okay, Gaurav. Because beta is a specific case of Dirichlet, right? So have you forgotten about this? So where do you use the beta distribution as a prior for? Coin toss like problems, right? Where the support is between 0 and 1, and where the probability of heads and probability of tails will sum up to 1. Support for Dirichlet distribution is x1 through xk. So instead of a 2 length vector, heads and tails, or success and failure, you have a k length vector, right? And where summation xi will be 1. Right? So you can think of beta as a specific case of Dirichlet with k equal to 2. Right? So therefore, they might have just implemented it, and you can also look at the PDF. Right? You can see that if you were to put k equal to 2, you will get exactly the beta distribution. Right? So it's a generalization of the beta distribution to higher k values. So wherever you are using beta as a prior for 2 class problems, you can use Dirichlet as a prior for k class problems. Right? So therefore, they would have implemented this in beta.pi. They just called Dirichlet.R sample. Right? Now you may want to go back into Dirichlet.R sample and see how it's implemented. They are doing Dirichlet underscore Dirichlet.apply concentration, etc. Right? So it's, you can always go to other distributions and see how, or if they have implemented the R sample method. So let's see maybe the Poisson distribution. So there's no R sample method. All distributions may not have it. Let's see if they have a sample method. They have a sample method. They don't have R sample method. Right? So all distributions may not easily have a reparameterized form. Coming back, so going forward, I think now we've seen 3 different variants. I would always suggest when we're doing it for the first time, when we are using VI for the first time, we should be looking at the reparameterization trick on our own. We should be implementing it ourselves. But after you've got sufficient confidence, you could just use R sample to reduce the amount of bugs with the lines of code that you write. Right? So now do you get how these things are related to the original formulation not being differentiable, right? Whereas the reparameterized formulation will show you the backpropagation path towards finding out the gradients for location and scale. And this is the central trick which gets used in variational inference, as well as the applications such as variational autoencoders or Bayesian neural networks with variational inference, and neural processes also. So we have not yet looked at the full neural processes things. We've only just looked at it as a decoder encoder architecture. We've not yet looked at the uncertainty angle there. So then I was trying to show you this problem where you have this mixture of Gaussians, and we've said that we need Monte Carlo sampling because to find the K divergence between any Q distribution and the mixture of Gaussians, because the analytical solution doesn't exist, and now we want to optimize it, right? To find the K divergence between two different families of distributions, what do we use? Monte Carlo sampling, right, to compute the K divergence. To optimize the parameters, what trick do we use? The reparameterization trick, right? So even for a trivial example like this, we need these two tricks, which will suffice for further more complicated examples. Right, so you can see that I've defined two loss functions. In one of them, I'm calling the R sample method. The other, I am just creating it myself. The reparameterization trick is done myself. And now can you see that the Q distribution looks like a fairly good fit to the mixture of Gaussians? You can also see this as an animation. So you can see how quickly we are able to come to a much better solution. You can see that the distribution Q is slightly becoming wider, which means that the height is reducing, and the location is also getting adjusted over the iterations. So typically you'll always want to see the loss going down, but sometimes the loss also increases a little bit. Some of this can also be explained by Monte Carlo sampling. Right, so now the loss is almost fixed, and we've seen that now the Q distribution seems like a very good fit for the P distribution, or a good approximation. Okay, any questions till now? So at this point in the previous class, we had also discussed elbow, which I'll want to discuss again because I think it's a slightly non-trivial topic. So we come back to the problem of Bayesian inference, which we are interested in. Is there a doubt? Okay. You can go ahead and ask.
Sir, I was thinking, why are we not able to find the grad for non-reparameterized?
So are you able to see why we are able to find out the gradient with respect to when we do the reparameterization? Because we are able to write it in the form of location plus scale into something, and then you can very easily find out the gradient with respect to location and scale. But once you sample, there is a random effect which is introduced. Right?
So, because we have an equation beforehand for the parameterized distribution.
So we've looked at this main problem in Bayesian inference is we have a posterior distribution, true posterior, which we never know, which is P of theta given D. We are saying that let's propose a guide or an approximate or a variational distribution Q of theta, which is parameterized by psi, right? And we want to get Q of psi to be as close as possible to P of theta given D, which we say that it's now an optimization problem. So we want to find out that optimal parameter psi star, which minimizes the K divergence between Q of theta parameters by psi and between P of theta given D. But what is the problem now? Why can't we directly go ahead and solve this optimization problem? Because P of theta given D is not known. If this were known, then we don't need to solve the problem. Right? We just directly use P of theta given D. Let's forget about the optimization problem and just look at the K divergence term. So this is the K divergence term, and I've expanded the definition of K divergence. Right? So at this point, can we rewrite P of theta given D, which is a posterior, using Bayes rule? Right? We looked at this last time also. We write that as P of D given theta likelihood times the prior P of theta and divided by P of D, the evidence term. So we just rewrite in terms of the Bayes rule. At this point, we can then write the KL divergence between Q and P of theta given D as an expectation of log of Q into Q of theta into PD divided by the joint P of D given theta and P theta. When they multiply it, they can be called as a joint distribution between D and theta, right? Now we can break down this log of this multiplications, right, into log of A into B we can write as log A plus log B. We break it that way. And now the expectation we want to compute over two terms. So we can break it by the linearity of expectation. What is the expectation over log of P of D? The same, because P of D is independent of psi. So we can therefore then write down this equation as KL divergence between Q theta and the posterior as the expected value over Q divided by the joint, log of Q over joint plus log of PD, right? PD term we typically call the evidence term. So we can call the log of PD term to be the log evidence, or sometimes we just call that as the evidence term also, the logarithmic of the evidence. Let's rewrite these things. What do we know about the KL divergence between any two distributions? Non-negative. Right. So if this is non-negative, and let's call this term as minus elbow of Q, right? So let's just call this term as minus elbow of Q. Now what can you say about P of D? The left hand side is greater than or equal to 0. This term is known as minus elbow of Q, and this is the log of PD term. Right? So what can you say about log PD term now? No, greater than or equal to elbow. So the left hand side is greater than or equal to 0, and you have a minus elbow term plus log PD. You take the minus elbow term on the other side. So you can then say it this way.
So log P of D will be less than
Okay, have written. So we have written KL divergence is greater than or equal to 0, and this term as minus elbow plus log PD. Yeah, I think I've made some mistakes in the signing or the specific minus.
yes sir. Yes sir, I have my because
So if this term is greater than or equal to 0,
so sir 0 is less or equal to minus elbow plus log P. And so if you move elbow to the left side, elbow less or equal to log P.
okay. Okay, so log PD greater than or equal to elbow, which also means that the evidence, which is log PD, is lower bounded by elbow, right? Evidence is at least as much as the elbow. So if we draw this diagram, I showed this diagram from this post last time. If we look at the elbow term, we add the KL divergence to it, right? Then we get the evidence term. The KL divergence can be 0 also, which is when the two distributions are exactly the same. So therefore, we cannot compute we don't know the posterior, but we can compute this term, the elbow term, right? So our original objective was to minimize KL divergence, right? Which means we can just rewrite that in terms of the elbow terms now, right? So minimize KL means maximize negative elbow or minimize elbow. Sorry, minimize negative elbow. we now look at some code where we're trying to compute this quantity, this expectation, right? So again, this expectation, if we have to compute, we have to use Monte Carlo sampling. We'll be going back to the coin toss problem. So I've just defined the log prior, log likelihood, log joint, and the true log posterior. So I've defined my log prior to be so my prior distribution is a beta 5,3. My log likelihood is just based on the Bernoulli distribution and the number of successes that you have. The log joint is log likelihood plus log prior. And the true log posterior we already know, which is the beta with 5 plus the number of successes, and the so 3 plus the number of times we get a tails. So there is some specific torch specific reason where I'm using validate args equal to false, because otherwise the back propagation was giving some issues with distribution, etc. And this is, I think, yet unresolved in PyTorch. It's an open issue. We can see if it gets resolved over time. Right. So the setup till now, it's what we have seen earlier also. Nothing new in that. Okay. So what is the new thing that we will now do in this setup? What is the goal in Bayesian inference? To compute the posterior. Here we know the true posterior, but let's assume we are not able to compute the true posterior. So therefore, we need to make a guide distribution Q, right, which has to be parameterized by psi. Right. What can be a good guide distribution here? You should know the answer. You should. I think you're overthinking. It's a simple question. What can you propose as a guide / variational distribution? Beta. You can also propose normal, right? Typically, beta would be better suited here because with normal you have to make certain other things. You have to go into the land of ADVI because you have to constrain the support to between 0 and 1. With normal, the support is not constrained between 0 and 1. With beta, it's constrained between 0 and 1. And fortunately for us, we have seen that the beta distribution also has a reparameterization. Right? So we can use Monte Carlo sampling and still be able to compute the parameters of beta this way, optimize the parameters of beta. Okay, can anyone tell me what I'm trying to show in this cell number 34? Let me show you the log likelihood also. Okay. So for log likelihood, what are the two parameters? Theta, whose shape is 1 cross 2. Why 1 cross 2? Theta is just the probability of heads. So it's a scalar. It's a scalar, right? And data is a vector which you give, which is, so data we had something like this. So the shape of data is 30. It's a vector of length 30 on anything you want to give. So log likelihood accepts as input a theta, which is a scalar. For that theta given a data set, you are able to find out the log probability of data, right? Now what am I trying to do in cell 34? This is cell 34. And why have I wrapped it in a try except block?
Like you're trying to so that like you maximize that approximately 17 by
Yeah, so that's my objective. I want to show that the log likelihood would peak at the MLA point, right? I want to show that. So I want to try it for different values of theta. I can write that in two ways. One, I write a for loop for theta I in theta values and then compute log likelihood of theta I comma data. That will work perfectly, but that is slow. So I was then trying to write LL equal to log likelihood over theta values and data. But now theta values is a vector, it's not a scalar. Whereas log likelihood wanted a scalar, right? So I want to basically loop over it. I can either write an explicit for loop out on the outside, or I can write something like this, which will fail, or I can call vmap, which we have shown earlier also. So it will think of this as it's a faster version of the for loop which is written to you. So for a which accepts theta as an argument and then it computes over the function log likelihood, right? So it will create a for loop over the theta dimension, and then you can give theta values over this. Right? So this is a much cleaner way to write than to write a for loop and much quicker way to write. Questions on this? So even if there are questions, I think you'll have to practice the usage of things like vmap, the usage of things like tree operations in order to be able to get more clarity over these. So we can then also plot the prior likelihood posterior, the true posterior. What do you observe from this? What do you observe from this plot? Anything? Very difficult or tired? Okay, Gaurav. Yeah, the likelihood is extremely, it seems to be flat, but because that's also because we're seeing in the linear scale. If we were to see it in the log scale, maybe we'll see sharper. We can see that the prior and posterior are quite different, right? And we have 30 data points. So if we have large data points, then the posterior will be more governed by the likelihood term. If we have very few points, then the posterior would be fairly similar to the prior, and that we can see here. Of the second plot, that is the log that is, I think, the likelihood of the log likelihood. Axis log likelihood. That is why it can go so low. So now we come back to the main problem in variational inference. We have to propose a target slash guide slash surrogate slash variational distribution, which we'll call Q. Typically, we call that Q as per convention. We said that let's propose it to be a beta distribution. So beta is parameterized by some alpha and beta. Now this problem boils down to optimize the value of alpha and beta, which minimizes the KL divergence between Q and the posterior, but we don't know the posterior. We'll not use the posterior. We'll just use the log likelihood and the log prior to get the log joint. So therefore, we'll have to compute the elbow term. And that is where we get the negative elbow term. We have the log joint function. We have the target distribution Q. We have to give some data, the number of Monte Carlo samples. Again, it's an expectation computed over Q. Right? The distribution over which we are computing the expectation with respect to computing is Q. Right? Therefore, you draw a sample from Q. I am directly calling the R sample method. Here it exists because it's a beta distribution, and we've seen that the reparameterization is existing. Then I'm computing log Q theta. Right? So if we go back and look at the elbow term, we sample from Q theta, we get n samples, n Monte Carlo samples. We plug those samples value in this log of Q of theta and in the log joint. and then we do log of this minus log of this, and you'll see that log of q theta is plug in those samples into q, log prob methods, and then the log joint, I'm again for the log joint also I'm creating a v map over the theta dimension, and then I'm computing it over the samples that I've got, right? So effectively just this is just Monte Carlo sampling. Generate n samples, n Monte Carlo samples from q theta, plug them into this expression, and then you take the mean over them. So 1 over n, that is the Monte Carlo expectation. Okay, what can you observe from cell 39 and 40 and conclude? The negative elbow method takes a log joint function, and then the next argument is the proposal, the target, the surrogate, or the variational distribution. Which of them is a better target distribution? The goal is to minimize negative elbow. Second one, and why does it make sense? Because that's the set of parameters you wanted to use, which is these parameters corresponded to the true posterior, right? So this is as good as you can get. We have created another, just a trainable model class, which is basically a wrapper around the beta distribution. This is again just to make it easier to reuse the train function which we have earlier. So in this case, we are giving the loss function as the negative elbow loss, right? Which does not need the full posterior, does not need the P of D term. You are seeing the alpha term, the beta term, and the loss term. One, you might notice that the loss has come down to be 21.3, which is fairly similar to this number that you had seen earlier, and still it's an optimization problem over Monte Carlo samples, so we may not be able to exactly match. But importantly, you can see that our learned posterior is fairly close now to the true posterior. Now here we have used our own implementation, but you can also use something like Pyro or NumPyro to do many of these things automatically for you. So in Pyro we need to specify two things, the model and the guide, right? So model is you can think of the data, so you can think of for the coin toss we have to specify a prior which we set to 5 and 3 earlier also, and then we are giving the likelihood term, right, how the data might have been sampled. So Pyro will automatically, using these pieces, these lines of code, automatically figure out the log prior term, the log likelihood term, the log joint term. It automatically figures that out, and then you have to specify the guide or the target or the surrogate distribution. You are telling that there are two parameters in it, alpha q and beta q, and you are telling their initial values 45, 45, and then you're saying that my theta is sampled as beta, right? So this is basically your q distribution. It's a beta of alpha comma beta distribution, and then you give this trace elbow method as the loss function. So it's basically elbow, but you give it trace because Pyro needs to do something like it needs to do some sophisticated machinery in order to obtain the log likelihood, the log priors, and the elbow terms, the guides parameters, etc. All of which we had ourselves done in an explicit fashion here. That needs to be done more hidden to the user in something like Pyro. They'll automatically figure out that is why it's called a tracing method. And then they call something known as a stochastic variational inference object. In the next class, we'll see how SVI differs from the typical VI that we are seeing. But essentially, you can think of this as the difference between SVI and the full batch variational inference to be that in stochastic variational inference, you can batch it over subsets of data, similar to how you do stochastic gradient descent. Right? You don't need to pass the entire data at once. You can pass mini batches of data. This will become clear in the next class. I don't want to be dealing into that today. But for now, just think of this as variational inference method, which accepts a model, a guide, an optimizer, and the loss. We run the optimizer over some number of steps, and you'll see that the alpha and the beta values that we'll get will be fairly comparable to what we had. Our implementation in this case turns out to be quicker. I don't know if you're missing out on certain tricks of using Pyro, or maybe because it's a very toy problem, the overhead of the tracing, etc., turns out to be more expensive. You had a question, Utkarsh?
When I was looking at the documentation of Pyros, and it was these were the methods for inference. Pyro is all about VI. There are other methods.
So Pyro has VI as well as MCMC, similar to NumPyro. They try and give you unified interface. They give you interfaces for things like predictive posterior, predictive class, which accepts these objects and then creates a predictive distribution object.
Basically, what we are trying to do is like we are trying to approximate the posterior. In this case, we knew that posterior would be beta, so we took QX as beta, and that way we were able to approximate it nicely, but it might not be the case. So, what if we had chosen normal, then our posterior would have not.
Yes, yes. So just for the recording, just to repeat the question for recording, Bhavesh's question is that in this case, we knew exactly everything about the problem setup. So we knew that the beta is the true posterior distribution. So we then made use of that fact and we use our guide distribution also as beta. And then we got good results and we are very happy over it for a very toy problem where we knew the analytical solution. So this, in typical practice, we generally don't know the target distribution. Many times, therefore, we end up using the normal distribution. For problem like coin toss, we just discussed that normal distribution is not a very good fit because its support is from minus infinity to infinity, whereas for the coin toss, it's between 0 and 1. So therefore, we end up applying something known as bijectors, which will constrain the support between 0 and 1. So there's an additional level of transform which you apply, which also means that you'll have to take care of the inverse transforms, etc., and how backprop will happen, and all of those things need to be considered, which is the topic which is known as ADVI. You do that automatic conversion to ensure the support over certain variables. Here it's between 0 and 1. For certain distributions, it's between 0 to infinity. Right? But generally, normal distribution ends up being the default choice in many cases. So Pyro also has things like auto guide. Let's look at some examples. No, I don't want to see this. And then one of the main question which comes when you try to use the normal distribution is that for let's say for neural networks, right? So there the posterior is over each of the weights spread across the different layers, right? And then what do you propose as the target distribution? Do you propose a huge, let's say you have a million parameters. Do you propose a multivariate normal distribution with a million parameters? That becomes very not in scale. That doesn't scale well because then you need a million mu vector, a million length mu vector, and a million cross million covariance matrix. So then people end up applying something like a mean field approximation, or you can just think of it as a diagonal approximation, where you say that your multivariate normal just is composed of independent univariate normals. For each parameter, you assume the posterior is a q, which is mu and sigma, normal of between mu and sigma. So it's again a big assumption that you take, and because of that, also you lose some some uncertainty. Right? You're not able to accurately capture all the uncertainty. And that's where most of the people, when they compare VI or Laplace approximation or other methods of quantifying uncertainty, they use the MCMC as a gold standard, because with MCMC, you know that with infinite samples under some conditions, that's the best you can get. So even though variational inference has a lot of very cool things, there are a lot of challenges also that you need to consider. Okay, for some reason the internet is not working well today. But essentially we can see, I was trying to show from their code something known as an auto guide. The auto guide will take the model, right? So if we can open this up, somehow I can show that. So the auto guide takes a model. So in the code that I showed, the Pyro code, I had to specify a guide, right? In their code, an auto guide, you wrap around a model object. It will figure out what are the different distributions and what are the different parameters. It will automatically assume each of them to be a normal distribution and then create an auto guide. Let's try with a different browser. Okay, doesn't seem to be working today. So then we can see that for both our implementation and the Pyro implementation, the results are quite matching to the true posterior. They're not exactly same because of certain ways in which Pyro differs and how maybe they're using SVA instead of the full batch variational inference. Or maybe we have not yet fully optimized it. But this was about a toy problem, which we'll very seldom encounter in practice. Let's come to a more realistic example of linear regression over which we want to compute.
There is some order like acceptance or rejections that goes in. Even if your proposal is not as important, you might still better get better samples from the underlying person. In this case, we're just taking the samples and like computing the expectation values. So why would this compare to like how I can maybe say the statistical
I didn't get the last part.
like this clearly won't work as well as say
This is so the question is that VI is unlikely to work as well as, it seems obvious that it's unlikely to work as well as MCMC. And we keep on making more and more assumptions, simplifying assumptions to scale. So why is it a fair comparison? Is that a question? So it's so MCMC is typically slow, right? So compared to this, it's slow. Here the sample, here also you do some sampling, but that is over a very simple normal distribution. There the sampling is much more involved and you have to make a proposal and you have to move in certain spaces. And this was the case some years back. But now if you look at many of the modern libraries, they run MCMC sampling over GPUs or over much more efficient hardware, which have made them very competitive. So you can, I'll probably send some post over the Slack channel also, which says that MCMC. So many people typically say that let's use VI because MCMC is very slow. I mean that's the general talk which goes in the community. But now MCMC is not that slow because we can run it on modern hardware with better implementations. But because typically people prefer optimization over sampling like problems, and VI will give you fairly good results fairly quickly, and it's mathematically also very neat, very convenient. So I think that's why a lot of people end up using. I don't know whether there's a unique single solution which works. In fact, a lot of the recent literature, a lot of the Bayesian literature, also now people keep questioning that do you need such complicated architectures, especially in the line of if you can just use some black box methods which can give you uncertainty estimates, right, and calibrated estimates. A lot of which is like, for example, in the recent literature, a lot of discussion is around conformal methods. Do you really need that amount of sophisticated Bayesian methods, or can you just use simple methods like, let's say, quantile regression, and just use some conformal methods on top of that to get calibrated, well calibrated uncertainty estimates. Because that was the whole objective we started all this analysis, all these methods with, right? We want to get well calibrated uncertainty estimates using our models, and our point predictor methods typically are either poor at that or they don't give that. For regression, you don't easily get the uncertainty estimates. You'll have to modify the likelihood, or you'll have to then use something more sophisticated. For classification, you do get the uncertainty via just the probability distribution vectors, but we saw that these methods are typically overconfident. Right? So it goes back to that entire discussion also, that Bayesian is not equal to probabilistic. We can have other methods which can give you these quantified uncertainty estimates, calibrated uncertainty estimates. And I think the floor is open in that sense, that a lot of people, a lot of competing policies, competing algorithms are being proposed every other day. We come back to linear regression now. So I'll generate 200 odd samples. Let me generate lesser samples. Right, I've generated some 20 odd samples. Again, I have to define the log prior, log likelihood, log joint. That is a typical practice if I am writing the code on my own. If I were to use Pyro, I just need to specify the forward pass in some sense, right? Using the model method. Let's see if, okay, this is still not working. Just trying now to open the web page. Come back to this. So we specify the log prior, log likelihood, log joint as we've done previously. And we also specify the negative elbow. Previously, the negative elbow was an easier definition. Here it's slightly more complicated, not much, because now previously you just had the coin tosses, you just had the y terms, you don't have the x terms. Here you have both x and y terms. So the log joint function itself now is accepting x and y. Previously it was not accepting, it was just accepting data terms. That's the only change I've made, negative joint. And then I've just created a learnable normal, pretty much what I'd shown earlier. Okay, so I'm learning, in this case, there are two methods that I'll be using. In the first, I am just learning a diagonal approximation to the covariance matrix. Right, so we've discussed that there are three types of covariance matrices that we can use. The first is a full covariance, the second is a diagonal, and the third is a spherical. Right, in diagonal you can have, so if it's a 2 by 2 matrix, we can have, in the diagonal version we'll have sigma 1 0 or sigma 1 0 0 sigma 2, whereas in the spherical we'll have sigma 0 0 sigma, and the full covariance will have sigma 1 sigma 1 sigma 2 sigma 1 sigma 2 and then sigma 2, oh, sorry, sigma 1 square. Right. So what can you see about the locations which is being learned? 3.1 and 3.4, right? Whereas if you see the generating function, it is 3x plus 4, right? Why do you think I'm unable to learn that? Can you close it? Why am I unable to learn the values 3 and 4 exactly? This is a Bayesian inference question, not specific to variational inference. Sorry? The number of samples is small, so therefore the prior will have an effect on the posterior, on the map, theta map, right? So very effectively, this is, you can think of this as the map solution in some way. We see the values 3.17, 3.4, and the scale is 0.21 and 0.08. If I do 1000 forward MC passes to predict, to get the predicted posterior now, so which is just, you get the 1000 samples and then you do Q of sample 0 dimension, which is the bias plus the bias plus the intercept into x. You can see that the fit is not very good, right? Because we had very few number of samples, right? So therefore the prior is having an effect. you can see some amount of uncertainty here. What uncertainty are we looking into here? Epistemic or aleatoric? So we're not looking into aleatoric uncertainty here. We're just looking at the epistemic or the model uncertainty. So we're looking at how much the different model parameters would cause. So uncertainty in the parameters is what we're looking at, right? P of theta given d, right? Which we're trying to approximate via the Q distribution. We have not really looked at the likelihood or the aleatoric component here. If we were to, instead of these number of samples, if we had more number of samples, 200 samples, everything else remains the same. You see the parameters are much more closer now, right, to the true parameters that we had. The price is still having some effect, but not as much. You can also see that the variance has reduced, right? Why does that make sense? What kind of uncertainty reduces when we increase the number of samples? Epistemic or aleatoric? Epistemic uncertainty can reduce when we have more samples. Aleatoric uncertainty, that's the definition. It does not reduce even if you increase the number of samples. Right? It's a irreducible uncertainty. And that you can see that the variance has not reduced as we've increased the number of points, and the theta map that we have obtained is closer to the true theta that we had. That is also reflected in the new line that we have. Right? The variance has reduced and the fit is also better. If we chose more diffuse prior, or we increase the number of samples, we will see the fit to become better and the variance to also reduce. But in this case, I am learning the diagonal approximation of the covariance matrix, or I am learning the covariance matrix with sigma 1 squared, 0, 0, sigma 2 squared. What if I want to learn the full covariance matrix? What do you think I can do? Can I learn the 4 parameters directly? Sorry? The covariance matrix has a restriction that it has to be positive semi-definite. Similar to the constraint which we had when we were dealing with the univariate case, it has to be a non-negative quantity. So there we did a soft plus over whatever we got, or we did an exponentiation. We need some similar operation here, or we create the covariance matrix from the square root, right? So you can think of the operation previously. If we got whatever raw scale, if we did a square of that for a univariate case, it becomes a valid number. Similarly, we need to take a square of something here, but we're not talking in terms of matrices. So we have to think in terms of the Cholesky decomposition and then do the square of it that way. So I'm showing for the full covariance matrix, I start with a parameter L flat, which is in this case a 4-length vector. I convert that 4-length vector into a 2 cross 2 matrix. I take an upper triangular matrix of that, and then I do the upper triangular is U. I do that U into U transpose. If I do it this way, then I am guaranteed to have a positive semi-definite and a valid covariance matrix. Everything else is the same in this piece of code. Now instead of learning 2 numbers, I am learning 4 numbers. And you can confirm that that these numbers 0.085 and 0.085 are indeed matching. So it's from that perspective, you can see this way of creating this covariance matrix is working. It's similar to the transforms we had done earlier for the univariate case. We either take the square, or we take the soft plus, or we take the exponentiation, or something, some variant of that. So here it seems that we have slightly more variance compared to what we had seen earlier. The model, it could also be due to not running for the same number of iterations. It will also be very well because of the case. Now we are considering a more broader version of finding out the variance. Instead of assuming the true parameters theta naught and theta 1 to be not correlated, we are assuming that there could be some correlation. Although that correlation is fairly weak, 0.06, but it's not exactly 0, right? So we are counting for more uncertainty this way, because there is some uncertainty which is mapping the relationship between the two, mapping the relationship between the two quantities also. So we'll stop here for the variational inference lecture. We still have 10 minutes. Are you up for a quick discussion on autoencoders or dead? Autoencoders is an easier topic, it's a more exciting topic. We'll not go into the variational aspects of autoencoder today, we'll just look at the regular autoencoder. The next lecture, we'll look at the variational aspects of autoencoders. Okay, how many of us know what an autoencoder is? Okay, can someone tell what you understand by an autoencoder?
I think it is a modern that comprises of both encoder and decoder.
Yeah. So there are various articles, various kinds of configurations. You typically assume that, so you have to, it's an autoencoder, which means it's the encoding and the decoding give you the same object. You start with an image, you give it to the encoder part, which then reduces it to a code or a latent representation. And then you have a decoder which starts from that latent representation, and then it gives you the reconstructed image. The loss function is typically the mean squared error between the output and the input, right? So you're able to do a good job at reconstruction if the output you are able to generate is the same as the input. So we typically have this architecture where we can think of this as a bottlenecking architecture. What we're trying to say is that can we reduce the information across multiple objects, multiple images into a latent dimension which is much smaller than the original dimension, right? If we don't do that, let's consider MNIST images. We have 28 cross 28 images, right? If we represent each image as a 784 dimensional object, we should be able to accurately decipher each and every image, right? But what we want to say is that, is there a lower representation or a low dimensional representation which can help us identify the different digits in MNIST, right? That way you're able to learn some structure in the data. If you're not able to do that, then you're not able to learn any structure in the data. We'd expect that all the zeros to have same latent representation in 2 dimensions, all the ones to have the same latent representation in 2 dimensions, right? So that is the whole idea behind autoencoders. One interesting thing you can do in this autoencoder like architecture is that once you've learned an autoencoder, you could throw away the encoder part, just feed some numbers to the decoder, some random inputs, some well-defined inputs, and you can create new objects. You can create new outputs, new images for MNIST like examples. So you can create generative models this way. Right? Let's look at the code for this. So I'm using the sign activation. As I had previously shown, you could use sigmoid, relu, whatever you want. I have created a very simple autoencoder object. It accepts any, in this case I'm working with images, and it accepts an image of input size. So I'll flatten it to 784 dimensions. This will be 784. Hidden size equal to 128, z equal to 2, which is the latent representation size, and then activation which I want to pass. So I have two networks, the encoder and the decoder. It's a very simple network that I've created. So my encoder goes from input to hidden size. Then I have an activation. Then it goes from hidden to the latent representation z. And my decoder is from z to hidden and hidden to input. And then I have a sigmoid. Because I'm dealing with images, I'm using a sigmoid because they're in between zeros and ones. And my forward is just the encoder and the decoder on the input. This is I'm using 1000 images from the MNIST dataset. I have put them on a scale of 0 to 1. I create an autoencoder object, input size is 784, hidden size is 128, and z equal to 32. As I've shown before, I typically want to see the model's prediction before I've done any training. So I have a reconstruction method which just calls the model of input x. I will just directly then plot these reconstructions. Right. So these are some 20 images that I've given, and the bottom images are the model's output for these inputs. Right. So clearly you can see that the model is untrained. Right. It's not able to reconstruct the input image. It's not able to. The autoencoder is not yet working. Okay, just 1 second. I think I need to do some changes. Okay, so there is an internal error that we're facing in the train function. I think we did some last minute changes like all of you also try to do for the demos, and sometimes things fail. So I can maybe just stop here. I can maybe just in a 2 minutes show what the notebook looked like and what we're trying to do. Right, so these are the images that I had with the untrained model. If I now train my model, you can see that the loss will go down as expected. And these are my reconstructions. Do they look impressive? Right? You were able to do quite a good job here. Next, I am using a convolutional autoencoder, which should be doing better because previously the autoencoding is using MLPs and which do not really have a notion of understanding of locality about images, etc. So in autoencoder, you have to carefully create encoder and the decoder. So my encoder is a bunch of convolution layers, activations convolution layers. Finally, I have a flattened to 784 dimension, and then from a linear layer from 784 to the number of latent dimension. In the decoder, I'll almost do the exact opposite. Instead of using con2D, I'll call con2D transpose. And this will have a lot more parameters typically. I am trying with different latent dimensions 2, 4, 8, 16, 32, 64, 128. And this is again the untrained model. This is the training losses with respect to different latent dimension. What do you observe from this? As you increase the number of latent dimensions, the reconstructions is bound to get better, right? Which is expected because now you're giving it more leeway. But you have to be careful about this. This is just the reconstruction loss over the train set. If you were to look at the reconstruction loss over the test set, that may not give you this pattern, right? That may have a pattern where the losses start increasing for higher latent dimensions. So the reconstructions over 2 dimensions, which is a really small number of dimensions, you're trying to somehow squeeze whatever information is in a 784 dimensional vector into 2 dimensional vector, is as expected not very good. With respect to 4, it's better. With respect to 8, it's even better. 16, 128, it's fairly good. At this point, I think the fun starts, and we look at this in the next class also. Now I'll kick out the encoder part. I will give some random inputs to the decoder, and I'll see what kind of reconstructions, what kind of images I can get. These are the some reconstructions I get from when I was using convolutional autoencoder with latent dimension 2. With 8, it does not even look like English at this point. And then I am looking at an interpolate method. So this is an interesting method. I take an image 1, and I take an image 2. I run them both through the encoder. I'll get their latent representation Z1 and Z2, and then I linearly interpolate between Z1 and Z2. So my first image is a 3 and my second image is a 0. I take the latent dimensions and then I interpolate linearly between them, and then I run the decoder through them. So you can see how the understanding is going from 3 to 0. It's not very good for this model because it seems like a very simple model. Whereas if you see for a more sophisticated model, okay, so actually the first image is a 5 and not a 0. So here I'm showing between 0 and 9. Can you see how neatly when it has to go from 0 to 9, it keeps on reducing some part here and keeps on adding some part here, etc. Right? So it's a very smooth interpolation. I am then showing a scatter plot when I'm using 2 latent dimensions of the 10 different digits. You can see that there are some regions which are being spanned by some of these points. And this is the hallucination plot which I want you to, which we'll discuss in the next class. This is over a 2-dimensional latent space that I'm showing, right? All the different objects that we can reconstruct. So this is where we'll start again. So we'll go over this again in the next lecture, and we'll see how the variational aspects can be brought in here. And after that, we'll see if we can cover something like, so either stochastic variational inference or neural processes.